Can we do? Shall I start?
Yeah, let me introduce you. So Jian is ESR of 5G, PhD candidate at Paris-Saclay University. So we are working quite closely. And this is a paper that he wrote for Cellular. Cellular is a conference that was held in last year in the US. And what essentially we try to do is to understand whether or not interference alignment that we'll introduce will give us any gain in a cellular network. So interference alignment is essentially a concept for coordinating base stations. And he's trying to use stochastic geometry to understand whether or not, if it brings any gain by taking into account the system overhead, the training overhead. Okay?
Okay. So good afternoon, everyone. My name is Jian Song. I'm from Paris-Saclay University and the Lab of Signals and Systems, which is an associated lab of CNRS, Superlab, and University of Paris. And today I'm going to deliver a presentation for the accepted paper entitled On the Feasibility of Interference Alignment in Ultra-Dense Millimeter Wave Cellular Networks. And as you see, this is a co-work by Marco and Tai and me. Okay, so we go to the first part. This paper is organized as follows, and in the first part, we answer 3 key questions to explain the motivation of this work, and in the next part, we put every key techniques and the key assumptions into our system models to explain some details, and then we summarize all the mathematical stuff in the system level performance evaluation section, and to capture some key parameters and explain our proposed models. And then we move to the numerical and the simulation results to compare our analytical results and the simulation results, and to see whether there are optimum values of system parameters exist. And then we conclude this presentation. Okay, so the first question is why we want to use millimeter wave. So the application of millimeter wave band can offer the considerable data rate which the 5G cellular system is expected to provide. If you look at this figure, it's a general architecture by 5G cellular system, and some key techniques are summarized inside. But in this study, we only focus on the network modeling behind the stochastic geometry. We will see how it works. The second question is why we want to use ultra-dense base stations. It's because in some studies we proved that the millimeter wave may outperform the conventional networks. This is mainly because the millimeter wave cellular networks is operated close to the noise-limited scenario, which is to say, compared with interference, the noise plays a dominant role. This comes from the large adopted bandwidth, such as 6 GHz or even larger. And but however, if there are some practical constraints, I suppose every one of you must know the bandwidth is very expensive source, and in this case, the performance will be deeply impaired. However, we still want to provide enough coverage to the mobile terminals. Then in this case, we need to increase the density of base stations, and the system is close to the interference limit. Okay, since the system is close to interference limited, and interference plays a dominant role, and how can we manage that? And IA, interference alignment, provide us the promising approach to deal with that, which is following. The K pairs of base stations are located closer to each other, and they cooperate and apply linear precoding techniques to suppress the strongest interference. Then, by doing this, and the coverage and rate may deeply increase. However, In order to do the interference alignment, we need to apply the channel state information at base stations, and acquire them it was obtained via the pilot signals, and pilot signals will cause overhead. That's the point. And in this study, the objective of this is to quantify the interference reduction versus the training overhead by pilot signals with our mathematical tools behind the stochastic geometry, and see how it may works and how system can be optimized. Okay, so next part is the system model. We summarize several key subsections as shown in the slides to explain how to model our networks, how to model the channel by taking into account all the factors for millimeter wave channel, and how to deal with the fadings and interference with aid of directional beamforming, and then we take into account the access technology based on cell association criteria, and next part we will explain the most important one, which is how to make the mathematical model computable, which is tractable also. And then we will explain how interference alignment with pilot overhead works in our proposed models. Okay, so the first part is a network modeling. We focus on the two-dimensional downlink scenario, and all the base stations are modeled as homogeneous Poisson point process with density lambda Vs, and we also assume all the mobile terminals are modeled as another homogeneous PPP with density lambda Mt. And since we are doing interference alignment, and then each base station and the mobile terminals are equipped with multiple transmit antennas and multiple receive antennas, by assuming they have the same transmit power for each base station. To explain it, we can go to this figure. This figure is generated by MATLAB. And this is one realization of PPP-based cellular network. As you may see, the typical mobile terminal is located at the region of the plane, and around them we generate a point according to homogeneous PPP, which means the number of base stations is distributed according to Poisson distribution, and the position of the points is uniformly distributed over the plane. And then we can count which one can be the serving base station for the mobile terminals, and what should be the interference of other base stations, and we will explain it later. And for our channel, we take into account the blockage modeling, which we consider two link states, which are line of sight and non-line of sight. We consider the probability of the link state as a function of R. This model is called multi-ball link state model. The objective of applying this is to make the proposed mathematical framework tractable, and we will see later. We also take into account the path loss model, and this is the power decay in path loss model, and Ks denotes the path loss constant for the link state S, and beta S denotes the path loss slope. We also take into account the shadowing, which obeys log normal distribution, which has a PDF is shown in the slides. As for the fading, we assume they are relay distributed. Then the power gain obeys exponential distribution with mean. We assume they equals to 1 for both loss link and non-loss link. Since the system is close to interference limited scenario, we apply the directional beamforming model to mitigate the impact of large-scale interference and fading to make our link more reliable. In this case, we apply two-lobe model, and Gmax means main lobe of the antenna gate of the main lobe, and Gmin means the antenna gate of the side lobe. And we apply the same for base station and mobile terminals. As for the intended link, we just multiply the maximum gain of GBS and GMT together as antenna gain of the intended link. As for the interfering link, there are 4 cases. It should be the main lobe of base station point to the main lobe of mobile terminals, and main lobe to the side lobes, and side lobe to the main lobe, and side lobe to the side lobes, as you may see in this figure. And the PDF of the interference scale is summarized here. By taking into account everything together, we need to select the serving base station, which obeys our proposed the cell association criterion, which accounts for the smallest pass loss and shadowing. We compute the every time when I speak in the pass loss, it accounts for the pass loss normalized by the shadowing, and we have all the pass loss for every base station to the typical mobile terminal. We just selected the smallest one as serving base station, and other base station in the play will generate interference. So we go back to the story of stochastic geometry, and what is the objective of that? How can we use that? The application of stochastic geometry is to simply use the intensity measure function, as you may see here and here. By using that, we can describe our proposed the performance metrics and some statistical characterizations. However, if we take into account the realistic link state model, such as listed in this table, the 3GPP, random shape, and others, it will make the intensity measure mathematically intractable. We cannot compute that. And in this case, we apply a model called a multiple model, and it was simply derived. It can be derived into a closed form for the approximated intensity measure. And by doing that, we can make our overall framework mathematically tractable. And as you see in the figure, it shows the general idea behind the multiple model, which means we divided the link between the mobile terminal and the base station to the multifractional regions. We have the different probabilities for some link states, say S, for different regions. Then overall, we sum it together, we can describe the overall link state S. In order to use the proposed model to describe the realistic model, we need to use the intensity matching approach, which means we match the realistic model to the target model. What is the target model? It's a multiple link state model and the multiple-based pass loss intensity measure, which is a function of the density of base stations and some parameters of multiple model. They are obtained by intensity matching approach. We solve that by deal with the minimum problem here by using the linear mean square error problem to obtain the parameters for D1, D2, D3, and the relevant parameters of the probabilities. Okay, then next I will explain how the interference alignment may impact our models. As I stated before, the interference alignment is implemented by the several cooperating base stations, and they form a cluster with a size K. And since we're using the multiple transmit antennas and receive antennas, and in order to make the IA feasible, we need to satisfy the constraint as shown here, which is NT plus NR should be greater than K k plus 1, and the minimum number of antennas should be greater than 2. And in this case, we assume there's only one data stream. Then, by doing the pilot overhead model here, we estimate how many time can be used for estimate the CSI, and how many times can be used for payload data transmission, which is two main part here and here. And how it's computed by justify how many time can be used for the payload data transmission. This figure comes from the Professor Andrew Lozano's paper. If you are interested in the story of interference alignment and overhead model, we can discuss later. Then we move to the system level performance evaluation part. First of all, we formulate our SNR model here by taking into account the every transmit power, antenna gain, path losses. By comparing the path losses of first one and the case one, we can justify which is the intra-cluster interference and the intercluster interference. And finally, we put it together to compute our model, which is potential throughput. And finally, after calculation, the potential throughput can be computed as a twofold integral with respect to the smallest pass loss and the case smallest pass loss. And we plug the moment generating function of aggregate interference here, which reflects the influence of interference and beamforming, and also the blockages here. As for the joint distribution of them, is formulated with what I stated before, the intensity measure. Okay, by regards the proposed performance metric, the potential throughput as a function of the different parameters, we can go to the numerical and the simulation part. We select the parameters according to Professor Rappaport's millimeter wave model, which corresponding to the 28 gigahertz carrier frequency, especially for the path loss slope and the path loss constant, and also the shadowing model. And here we apply the realistic model as a random shape, and we do in the intensity matching, and we can obtain the multi-ball model, which means the different radius of the ball should be like here, and the probability of line of sight is obtained as well. Whereas the intensity matching, from this parameter we can fully describe the realistic model here is random shape. As you may see, you can from the region 4.7 meter to 18.6 meters, we can see approximately it was 0.36 percent of the link are line of sight, and yes, if we calculate the non-line of sight probability for this region, we simply computed it by 1 minus this value here. Then we plotted our figure potential throughput with a function of RCL. RCL describes the density of base stations. Every time we plotted our mathematical model with solid line here, we validated it against Monte Carlo simulations. And in this figure, we compare the different cluster sizes here for k equals to 1, which means no interference alignment applied here. And we go to the cluster size up to 24. And as you can see in this figure, for each cluster size, there is the optimum value of the potential throughput, which corresponding to the optimum cell radius, which is the density of base stations. Then we selected the peak value here in this figure and plot it against the cluster size. We can have the figure 2 here, and as you may see, the peak value appears for the cluster size equal to 7. Okay, so in this paper, we propose tractable mathematical frameworks originate from the intensity matching approach. And as you may see from the figure 1 and the figure 2, due to the blockage, there is an optimum density of base stations which can maximize the potential throughput. And due to the channel state information overhead, we can find the optimum value of cluster size which can maximize the potential throughput in figure 2 here. And in our parameters, we proved that the maximum gain of IA is 0.7 bits per second per hertz for the cluster size equal to 7. And if you are interested in this topic, and more details are summarized in the reference list here, which gives us a general idea behind the stochastic geometry and the millimeter waves, and also the general topic of interference alignment. Okay, so thank you for your attention. And any questions so far?
Okay. I will not ask about the content because I'm mathematically overwhelmed. Yeah.
Yes, also.
Me too. No. Okay. Basic thing. I think the presentation, I mean, the way you presented was correct. I mean, but perhaps I missed just stressing those interesting things. You provided a lot of information, yeah?
Yeah.
And you provided a lot of details on the models, etc. That's okay. That's okay. I understand. I guess that for the experts on the topic, this is important because depending on how you model that, it's tractable or not, and then assumptions apply or not. So I'm not against that because probably it's needed. The problem is that, for instance, I went through the whole presentation waiting for the results because, to be honest, I mean, mathematicals were very complex. So I was expecting some results like saying, okay, here you have the contribution. And perhaps you missed, like, you described the curves, but you didn't provide the outcome. I don't know if I explained myself. I saw that as you increase the number of clustered cells, okay, there was a trade, for instance, you didn't say there was a trade-off because as you increased the number of cells in the cluster, you improved that metric, but at the end when there were too many, you went back. So, but these kind of trade-offs are interesting to be explained. I mean, because everybody can see, I mean, for instance, I don't know about the topic, but I could understand the figures. So I was expecting some more outcome, yeah? And going into the, let's say, the mathematics,
yeah.
Okay, I understand that you need mathematics because the model is important as a work, as a contribution, but perhaps you could reconsider the way you include them in the slides. For instance, I had the feeling in some slides, for instance in 16 and 15, like you were trying to use all the available space. So there was just a formula out there, some others here. As you had some remaining space, here. As you had some remaining space there in the right side, okay, I put another one. So, you know, I mean, I understand, and perhaps some of them perhaps could be simply defined without the expression. I'm not sure. I'm not sure. but for sure perhaps organized in a different way. And another thing that, two more things.
Yeah.
At the beginning, beginning, DA.
Oh, this one?
Yeah. Was it necessary to include, I mean, what did you try to explain here?
I try to explain how, what's the general PPP-based cellular network.
And do you need to include a circle with 8 kilometers of diameter?
Yes.
Do you see my point? I mean, sometimes it's enough by including, let's say,
Just a several point around.
yeah,
the,
just you included some figures that are, for instance, easier to understand afterwards.
Okay.
Yeah, because it's a I mean, the number of points is under control, something like that. And then the very last thing I had, something I couldn't understand. First of all, you introduce the interference alignment concept.
Yeah.
Yeah, that's right. And then you forget about that. Okay, you forget about that. And when you go to the system model, you explain it again. But the explanation you include there has nothing to do with stochastic geometry. My question is, why not including these when you explain interference alignment? So first of all, you provide information to the non-experts about the interference alignment. So, okay, this is interference alignment, this is the way it works, this is the overhead, etc. Because you talk about the overhead before. And then once you have that, we understood that, and then you go to the system model, and if this has a consequence in the formulation, you can say, look, here is where I...
Okay, so do you mean we can explain that in directly to the model, and which part is it?
What I say is that if you have to explain I mean, if you have a concept, try to explain it. I mean, to put all together. And, all together.
Okay, instead of just...
unless, obviously, if, for instance, if you explain interference alignment from a general point of view,
yes,
and then when you go to the system model, you need to explain some details because they are connected to the stochastic geometry, and you have just explained stochastic geometry, I could understand that. I mean, okay, look, what I explained about interference alignment is translated into this in this model. But to be honest, I didn't understand why you split it up.
Okay.
For the,
but it was we wrote it into the different sections. Maybe that's the point.
Yeah,
I should be noticed.
What you have to take into account that sometimes the structure of the paper and the structure of the presentation does not necessarily. It's not necessarily the same.
Okay.
Yeah. But okay, the presentation was good and the results as well. But perhaps you should explain a little bit more.
Yes.
Yeah.
Or should we explain that in a correct way?
No, I'm not saying it's not correct. Eh? it's okay. But okay, with some minor changes.
So other comments.
Thank you.
Go ahead. Okay, let's start to see who didn't ask any questions. Okay.
Yeah. Another question, just a remark for the slide 29. Oh, 29, no, 19.
19. Oh,
19. Yeah, the lines in yellow and green,
yes,
we can't see them.
Okay.
And the stars line, we can't really understand.
Not that visible.
Yeah. So just this. Yeah, just remarks for the too much information in some slides.
Okay.
And that's it. Otherwise, I think it was correct. It was okay.
Okay.
Yeah.
Okay. Thank you.
Just one question about this intimidating slide number 16.
16.
Good definition.
This one?
If I get this correctly, just help me go this way. If I get this correctly, you use the moment generating function to get the expected value of the interference.
Yeah.
And so the reason you have the moment generating function is because you use the Laplace transform of all different interferences and obtain the moment generating function of that.
Yes.
Okay, that I was able to follow, but still, I don't know, when you were describing the way this, can you please elaborate a bit more exactly what happens with this what I see here, because I got a bit lost. If you could just say it again, exactly what is what.
Okay, since we compute the average over the interference, due to the interference alignment, there are the intra-cluster interference and the inter-cluster interference. We have the estimate of each part, and when we compute the moment generating function by using Laplace transform and compute the average for each part, then we can plug the
Yeah, that is, I don't follow which thing is nested where. I don't know which thing goes where. Like the first function is doing, the red function is doing what then?
Yes, the red function is the general one, the target framework, and yes, we can plug here.
Yeah.
That we change the variable z here with this one, and inside here, as you may see, there is m, where m equals to here, and m inter equals to here.
And the blockage was where?
Blockage is here.
And you put it, where do you put that?
We substitute this equation here to here and here.
You put you have then the moment generating function with the blockage into account.
Because blockage model are plugged inside the intensity measure function. We compute the derivative, then it also contains that. We plug that inside the moment generating function by using the probability generating function behind the stochastic geometry. By doing that, we can derive step by step, then we can get the final results here. It's a long story. If you are interested, we can discuss later.
Let me try to give an hint on the system model, so you will be able to get. So essentially, then I will give you my comments, okay?
Okay.
After. So the point is that this is essentially the potential throughputs. So what we say is that there is a threshold for decoding the packets, which is gamma TH, and so essentially you can decode the packet if your SINR is greater than this threshold, which means that at minimum you can get this threshold, this rate. So this is the rate that you can get in the worst case, multiplied by all the rest, which is the probability that you are greater than this threshold. Okay. This tau is the training overhead, so how much pilots you need to transmit in order to estimate the channel state information. Okay, in the IADA slide, where there was this time slots, where there is pilot transmission, data transmission, pilot and data transmission, this one. So essentially this tau takes into account how many pilots you are transmitting in your block, okay, your coherence time, if you want. That's essentially the idea. Go back to the slide. Yeah. The reason why what it says is that you are applying interference alignment on a cluster, so on K base stations. Usually, if you apply interference alignment of K base stations, you should remove all the interference intra-cluster. So this should not be there. But the point is that we have taken into account the channel estimation errors. So if you have channel estimation errors, you are not able to cancel completely the interference inside the cluster, but you take into account that you have also some residual interference. So this part tells you the interference that originates from the imperfect channel state information that you are able to estimate, because we take into account an estimation based on the MMSE. Okay, during the pilot, you receive the pilot, so you estimate it, but there is noise. So the estimation is not exact. If the estimation is exact, this is going to go to 1 as a moment generating function. This, on the other hand, is the intercell interference, which means that all the base stations outside your cluster that are always there, assuming the full frequency reuse. So everybody is essentially transmitting outside the cluster. This is essentially the meaning of this thing. And this is the PDF of the closest, this is the joint PDF of all essentially the base stations in the cluster. And it can be shown that what you need is the base station, the distance of the closest base station, and the K, the number K, so the last in your cluster. If you have 10 base stations, what matters is the first one and number 10. That's essentially what can be shown. That's the reason why you have only two variables here. Okay. So essentially, this is the impact of noise. This is the imperfect channel state information. This is the rate that you can achieve at this threshold. Training overhead impact of intercluster interference, and this is impact of intercluster interference. This is the association probability. This is essentially what this tells you.
Yeah.
All the rest is essentially details that takes into account this blockage probability in order to take into account this millimeter wave channel that says that you can be in line of sight and in non-line of sight. Okay. The rest is essentially all details. The most complicated part was essentially this one. If you look at the conventional stochastic geometry, because you need to take into account the cluster, and so in some sense you need to take into account the joint probability distribution inside the clusters of the base stations. Otherwise, I mean, the approach is standard.
Yeah.
This is essentially the only thing that changes. Okay, that's more or less the idea. Correct?
Yeah.
Go ahead.
My question was on slide 19 again. I was a bit surprised when I saw the markers here because they're very, how to say, they're very crowded on this area 20, and then they get very sparse. But is there an explanation? Did you do it on purpose? Yes, because they're very sparse.
Because we choose a different step size in the computational mathematical model and also the Monte Carlo simulation.
Because there it was the area that we're mostly interested, so it was more packed.
Yeah.
Okay,
If
okay.
we always choose a very dense marks here, we choose dense value and the dense step size here, it will take lots of time. Almost
Okay,
it will
okay.
take the whole life.
Okay, okay, that was uncovered.
In the next slide,
Yes.
the next slide is the same reason here why there's this huge gap between the 8th and the 24th. The gap there is no data between the 8th, k equal 8 and k equal 24, it seems.
K equal to 8, k equal to 24.
There is no data between these two values. Is the same reason?
Yeah.
Essentially, I mean, when we reach the optimum.
Yes, because the cluster size we choose is at the beginning we choose k equals to 1, 2, 3, 4, and we just selected the first one and selected the last one. The last one means we can ensure that tau is greater than 0, which corresponding to k equals to 28.
Essentially, I mean, there is no reason why there are markers or not. It's just essentially you reach the maximum, and then we said that we don't need the.
So the point is that you can guarantee that that's the maximum.
Yeah, because I mean we from the previous figure essentially. From the previous figure, so where you can see the many markers. We'll go back to the slide. So what he didn't explain is that figure is obtained from this one by picking the density corresponding to the maximum. So the reason why we can make sure that we pick the maximum is the question that Nikos asked. It's because essentially we are very fine in computing the things, so we can essentially identify the maximum. And the next slide is go to the next slide. This one is the look at this maximum PT. If you go to the previous slides, go to the previous slides.
Yes, the peak.
This is the
peak.
PT corresponding to the peak. That's the reason why we essentially plot this one. So it's K1 corresponding is the value corresponding to the lambda star here for K1, K3, K5, K7,
And 24.
K24. The reason why it's K24. Let me say something a little bit before. So go to the slides where there is this one. Yeah, this one. So essentially, if you make your pilot very long, you can estimate your chamber state information very well, and also you can make your cluster huge. So it means that you can remove all the interference. The problem is that you spend a lot of time for the overhead. So essentially, there is that peak. There are some cases where you can make your cluster size so big that in some sense you don't have any payload available, because we fixed this one.
Okay.
This is fixed. And then if you keep this big at a given point, this can be negative. So 24 is essentially the biggest cluster size that you can support for that block size, for that coherence time.
Okay.
That's essentially the reason why we stopped at 24. Okay.
No, I mean, stopping at 24 is fine. I mean, you can. I mean, that's the explanation why you stop at 24. But I wondered at the beginning why you just jumped from 7. To
Yeah.
24
This is the
instead of-
This is essentially the maximum pitting.
Okay.
Other questions? Okay, some comments. Jian.
Yeah.
So, I think that we need to redo the presentations entirely. So I didn't. So you sent me the presentations, and I didn't want to give you comments because otherwise it would have been unfair. Let's say. So to do the objective of this session this afternoon was that you come here without any comments, without any feedback. We give you your presentation, then we tell you what you need to modify. Okay. So that's the reason I didn't send you any comments about the presentations. I think that your general approach to the presentation should be different. I mean, stochastic geometry is not the main objective. Stochastic geometry is a tool that allows you to solve a problem. So you should focus your presentation on the problem that you need to solve.
Okay.
The problem was, does interference alignment make sense? So the gain that we get from the reducing the interference is worth in terms of overhead that we have in the channel state information estimation. This was the general problem. And then, I mean, you can formulate, but it's better that you elaborate the problem from this, with some figures. Because, I mean, if you start putting a figure about interference alignment with the base stations that collaborate, that you have a cluster, that this cluster can reduce interference, that makes things much, much better.
Okay. Do
So
you mean the realization and generated?
Yeah.
Yes, we should put something like around the typical mobile terminal by. Yes.
For example, this can be more useful according to also what Ferran said. No? So you have a base station, you remove the signals, and you try to show. So if you look at the presentation that I presented the same things as Cellular. I presented this as Cellular. If you see my presentation, it's totally different from this.
Yeah.
Completely different. So you need to try to sell this story a little bit more. You need to reduce a lot of mathematics because it's not worth it. I mean, so you need to go to the point. For example, you know all the questions that they asked. So this is the point where you should have focused your presentation. To really say we want to study this overhead and we want to do this kind of things. Okay, that it's the first time that you give a presentation, so it's normal. Okay, it's not a big problem. But this was essentially the objective. So to let you understand that these are the things that you need to focus on. From the technical point of view, 90% of your presentation was sound. 10% of the presentation for those who are expert in stochastic geometry was not. Something must be improved. Okay. So without going into the details, but for example, if you go to the slide of the multiple, the matching or the intensity matching, it's not totally correct when you say that this is stochastic geometry. This has nothing to do with stochastic geometry. That's an approximation that goes far beyond from stochastic geometry. Okay.
Okay.
So you need to. 90% of the talk was correct, but there is 10% of the talks for those people who are expert in stochastic geometry that could be a little bit misunderstood. Okay. And the other thing is, forget the paper, because as Ferran said, as also Leonardo said yesterday, the paper is written in a way. The presentation should be made in a different way. Okay, that's essentially the point. So you need to work a little bit more on the way that you present the things. Okay, and take inspirations from the comments that they asked, because if they ask you these questions, it means that these should have been the things to focus on. Okay. For the rest, I mean, it's okay. I mean, but you need to change a few things. Okay. Questions? No.
Thank you.
All right. So I think that we have done for the technical